everyone. I am absolutely thrilled to have you here today as we continue building your machine learning confidence from absolute zero. So if you recall, back in part 3, we explored logistic regression to handle our classification tasks. But today we are exploring a truly powerful algorithm. It's one that can actually handle both classification and regression, and it does so with this remarkable clarity because, honestly, it thinks exactly like a human being.
Okay, let's dive right into this. Have you ever played the game 20 Questions? You know the one where you ask a series of yes or no questions, usually getting increasingly desperate until you finally narrow it down and guess the correct answer? Well, that is exactly how our topic for today, the decision tree, works. It asks questions, it narrows things down, and it gives an answer. It is genuinely one of the most intuitive models out there. Really quickly, here is our roadmap for today's explainer. 1. The 20 Questions algorithm. 2. Anatomy of a decision tree. 3. How do trees learn? 4. Code and decision boundaries. 5. The pros and cons. And finally, 6. Real-world applications. Let's kick things off with section 1, the 20 Questions algorithm, thinking like a human. So what exactly is a decision tree? Basically, it's a supervised machine learning algorithm that's incredibly versatile, simply because it handles both classification and regression. But here is the absolute best part for beginners. It doesn't really care how messy or weirdly distributed your data is. It just works exactly like a flowchart. The logic simply flows from top to bottom, making it one of the absolute most intuitive models you can use for capturing those complex, nonlinear relationships in your data. Moving right along to section 2, anatomy of a decision tree, mapping the logic. Now, what's really interesting here is the terminology. Think about asking that very first wide net question in a parlor game, something like, is it an animal? You always start at a single point, at the very top. In machine learning, we call this the root node. It's the absolute beginning of our flowchart where the initial feature test actually happens. So, based on the answer to that very first question at the root node, you travel down the pathways. We call these branches. Essentially, you're going left for yes or right for no. And these branches lead you down to what we call internal nodes. At these internal nodes, well, more feature tests happen. The algorithm just keeps recursively asking questions, splitting the data further and further down the branches. And it just keeps doing this, right? The algorithm keeps asking these questions and traveling down the branches until it finally reaches the very bottom. This definitive bottom point is called the leaf node. It represents the final answer, the ultimate prediction, or the output. Once you hit a leaf, that's it. No more questions are asked. Section 3, how do trees learn? Finding the best split. Okay, so the flowchart structure makes total sense, right? But how does the machine actually decide which questions to ask? Well, the algorithm simply looks at all the features in your data and asks itself this exact mathematical question. Which feature best splits the data into pure groups? To answer this, the tree relies on a mathematical concept called entropy. Now, please don't let the math scare you off here. Entropy is simply a measure of impurity, disorder, or basically messiness in a dataset. Think of it exactly like a playroom with toys scattered everywhere. The tree's whole job is to organize them perfectly. So, when it calculates this, if the entropy equals 0, it means the data is perfectly pure. Everybody in that specific group belongs to the exact same category. There is a whole formula for this involving probabilities and logarithms, but honestly, you don't need to memorize the math right now. Conceptually, just remember this. 0 means perfect purity. On the flip side, an entropy of 1, that means your data is perfectly mixed. It's a complete 50-50 split. This acts as the absolute worst-case scenario for making a clear decision, because it means the group is as messy and disordered as humanly possible. The algorithm wants to run away from 1 and get as close to 0 as it can. So the crucial point is, how do we actually measure that journey from a messy 1 down to a pure 0? We do it with something called information gain. Simply put, this calculates how much a specific feature actually reduces that messiness after a split. The algorithm tests them all out, and the feature with the highest information gain wins. And it just repeats this recursively until the leaves are pure or some other stopping condition is met. Which brings us to section 4, code and decision boundaries, seeing it in action. Now, actually doing this in practice isn't magic, it's just code and a bit of geometry.
And this brilliantly illustrates the geometric difference between our models. Unlike logistic regression, which, draws straight-line boundaries through the data, decision trees divide the feature space into complex rectangular regions. By doing this, decision trees can capture these highly complex, nonlinear patterns that straight lines literally just miss.
Let's look at how this plays out in a simple Python implementation. Imagine a data array of age and salary used to predict a target. Using this scikit-learn library, you just import train test split and decision tree classifier. You pass in this data array X and your target Y, split it all into training and testing sets, and then simply call model.fit to train it and model.predict to test it. With just a few lines of code, you can print out your accuracy score. It is incredibly approachable if you're just starting out. But when you write that code, you have the option to tweak certain settings, which we call hyperparameters. You can change the criterion to set your splitting function to either Gini or Entropy. You could adjust min samples split, min samples leaf, and max features. But I want to explicitly warn you about max depth. This one controls the maximum depth of the tree. You absolutely must use this to prevent the model from asking way too many questions and getting totally out of hand. Actually, if you don't limit it, the tree will just memorize your data rather than actually learning the underlying patterns.
Section 5. The pros and cons, the good and the bad. All right, let's do a quick impartial review of why data scientists absolutely love this specific model, alongside where it can fall dangerously short. First off, the advantages are massive. Unlike models such as SVM and KNN, no feature scaling is required whatsoever. It works naturally with both categorical and numerical features. It handles nonlinear data effortlessly. You also automatically get feature importance, so it tells you exactly which questions were the most valuable. And best of all, the resulting flowchart is so easy to understand and visualize that even completely non-technical stakeholders can read it perfectly. But we've got to talk about the downsides. The biggest disadvantage by far is the overfitting problem. Trees can grow far too deep and overfit by literally just memorizing the training data, meaning they require pruning to stay accurate on new unseen data. Furthermore, they are highly unstable. Even a tiny tweak to the underlying data can completely destabilize and rewrite the tree's entire structure. They can also become overly complex and highly biased toward dominant classes if you're working with imbalanced data sets.
Section 6. Real-world applications, making an impact.
Let's move along and see how this builds our understanding by looking at some real-world use cases. Imagine a banker deciding whether a person should get a loan. A decision tree can quickly analyze the applicant's features to predict approval. Or think of a doctor trying to figure out what condition a patient has. The tree acts as this brilliant diagnostic flowchart. From detecting fraudulent transactions to grouping customers into segments, deciding what exact crops to plant in agriculture, or even figuring out what product a recommendation system should show you next, industries rely heavily on this algorithm to make sense of their data. Ultimately, decision trees are beautiful because they are incredibly transparent algorithms. This transparency makes it possible to trace exactly why a machine made a decision, step by step. In fields like medicine, finance, and law, where decisions absolutely must be explained to humans, fulfilling that critical legal and ethical need for explainability is paramount. You just can't get away with a black box model in those fields. So we know it's intuitive, transparent, and powerful, but how do we solve that fatal flaw of overfitting? Well, what if instead of relying on just one single tree that might memorize the data, we combined hundreds of trees together to make stronger, far more accurate predictions? That is exactly what we will do in part 5 when we explored the random forest algorithm. Be sure to subscribe right now so you don't miss that next explainer. Keep learning, and I'll see you there.